forgot the thing you want to talk about? No, we're good. Boy, no, not at all, huh? Christian?
I don't know. I don't really know if I want to talk about it. But, it's the last question on the homework.
Yeah, the one for today. Yeah.
So much time on it.
Which one was it?
Progress. It was I think it was like 1714. It said it like laid out a function where for rational numbers where it was like x took the form p over q, and p and q were both just different integers with q not being 0. The function would like just turn those into 1 over q.
Yeah.
And then for irrational numbers, like it would just become 0, and you had to like prove that the function was continuous at each irrational point and discontinuous at all the rational
Yeah.
points. And I feel like I know what I need, like what I'm supposed to do. I just can't figure out how to write it.
Let's talk about it a little bit. It's funny because I forgot I actually signed. I guess I'm like shocked that I signed that, but I'm glad. But I was like I kind of was like, we need to talk about Thomae's function today, because that's what this function is. So let's talk about it a little bit. And I think it's this one. Just let me know if this is in simplest form. I think it's simplest form. Or just P over Q. It doesn't say simplest form, does it? It just says Q is not 0.
And then I think it was simplest form.
That makes sense, because otherwise it could be ill-defined. Yeah.
And then f of 0 was 1. That was the last.
And, oh, okay, cool. So let's kind of look this out. This is an awesome function, by the way. Did they restrict, it's just all reals.
Yeah.
It's just across the real line. And the thing here was to show that x is continuous at the irrational points.
Yep.
Which is kind of crazy. Just real quick, real analysis friends. What's an example of a function that's nowhere continuous?
I can't remember how to pronounce it. With the Dirichlet function?
Dirichlet. What is that function?
It was 0 at the irrational points.
Yeah.
And 1 at the rationals, I think.
Yeah, that sounds good to me. So, and you can honestly do it in either order. I've seen it kind of gone both ways. So 1 if x is irrational, 0 if x is rational. That's good. Nowhere continuous. I like it. Can somebody give me an example? Somebody else besides Mr. Christian. It's already always good to just go for the low-hanging fruit as soon as possible, because it just gets deeper after that. That's what I do. Like when we put like volunteer sheets up in the math department, I'm like, sign me up. I'm signing up for the easiest fucking thing I can find on this list. The thing I want to do. Can someone give me an example of one that's continuous at exactly 1 point and nowhere else? To find out all the reals. Yes, Ms. Liv.
It would be like if x is rational and 0 if x is irrational.
Yeah, perfect. We could take x times the Dirichlet function, which is equal to x if x is irrational. Do you remember where that was continuous, Liv?
At 0.
Yeah, continuous only at the origin. Kind of, even though you've got this crazy fuzziness going on, the fuzziness piles up. Everything kind of comes together at the origin and only at the origin. So that's kind of cool. Nice. Now we've got a function that is claimed to be continuous only on the irrationals. So I have kind of an interesting question that's somewhere in here. It seems like we skipped some things, right? We went from nowhere continuous, one-where continuous. Why don't we have countably continuous? So here's a question I just kind of want to put out there to you is, can we have a function that is continuous only on the rationals? Seems like we should be able to. Here we got none, here we got one, now we got uncountably. That is continuous. So that's a deeper question. I kind of leave that. If you're interested in exploring that, check it out. I'll address it again on Wednesday. Not like you're probably going to do a lot of research between now and Wednesday, but you might. I know some of you might. So this one is pretty weird. Yeah, this is called a Thomae's function, which is kind of a cool name. Sticks in your head. That's why I called it T. So let's check this thing out. So it's dead at every irrational point. So these are all going to be, we can't draw that, of course, but we got a bunch of zeros, so I'm just going to scratch that thing up so it looks like I took out the irrationals. And then it's going to be 1 right at the origin. Okay, cool. Awesome. And then it looks pretty weird otherwise. So let's look at some examples. So if I ask what is T of 1/5, that's just going to be 1/5. If I ask what's T of 2/5, that's also 1/5. If I ask T of K over 5, it doesn't matter what that multiple of 5 is, it's still 1/5. Unless, yeah, but we have to go to simplest form here. So I guess if K is less than 5. As soon as K is 5, we've got T of 1. What's T of an integer? It seems like it'd just be 1. Do you see that? Because an integer can be written as a rational with a 1 as its denominator. So if I have T of n, that's just n over T of n over 1. That's just 1. So at every integer point, we're also going to be back up at that 1. So 1, 2, 1. How did you get some of this stuff going, Christian, when you were? Yeah, kind of grokked some of that a little bit. But what's happening everywhere else? Well, anywhere you could get a fraction with a specific denominator, so we're taking this, going to 1 over q, I can achieve any fraction. So I can get 1/2, 1/3, 1/4 as all my outputs. So somewhere in here, I'm going to have those things. For example, exactly at 1/2. I'm going to put out 1/2, exactly at 1/3. I'm going to put out 1/3. But also 2/3 looks exactly like 1/3. This was my 1/2 here. 1/5, 1/4 looks exactly like 3/4, I guess. Let's see, what are all the options? 2/4 would go to 1/2, so that would just, once we're at 1/2, we already know that comes out to 1/2, and 3/4 goes to 1/4. So it depends on how things cancel, but you've essentially got these little bitty dots building these triangles. You're gonna have your highest point at that halfway mark. So for example, at 3/2, you're gonna get your 1/2. At 5/2, you're gonna get your 1/2. And you're gonna get the same pattern to repeat over and over again, so you've got these weird fuzzy triangles kind of inside there. But then there's a lot of other stuff going on. Let's take a look at an irrational. So what were you thinking about the irrationals? I think because it told us that it's continuous there, right? So did you come up with an argument as to why that might be?
Not a good argument, but I was kind of thinking about how, so as far as like cardinality, the rationals are countably infinite.
Yes. Correct.
And the irrationals would be like uncountably infinite.
Yes, sir.
Okay, so I don't know if this is right, but I was kind of like trying to use a base idea that like if the irrationals were uncountably infinite, then maybe there would be like, I guess, what I had looked up kind of said that like more or less dense isn't really like a term to use.
I know what you mean, though. We know what you mean.
Yeah, kind of like that idea
Yeah.
that like if you were gonna use like a rational point, like if you pick any rational point, any I guess delta like ball or like neighborhood of points around like that x would also contain an irrational point that would jump back down to 0, and that's why it would be discontinuous at like the rational points, but then like kind of like on the opposite side, for the irrational points you could choose like kind of some like delta neighborhood, I guess, of like x inputs where you'd have like for any irrational point like an irrational on either side, so that would be continuous at that point if like things kind of like lead that way. I don't know, that was kind of like the base idea that I was trying to use, but I couldn't really reason it out further than that. I got a little bit of like headway going on like proving that irrationals were discontinuous with the epsilon and delta.
That's pain. I'll tell you what, that is probably the most painful route. So that's
Really?
cool that you were like headed down that route, because that to me it would be like really stressful in a way.
I had kind of thought I figured something out
Yeah.
with like the idea that when you plug in if you were to choose like let x be a rational number, and say that for like I might just read what I have.
Okay, alright.
So I said that like for if x is a rational number, for any delta greater than 0, the interval x minus delta to x plus delta would contain infinitely many like alpha points that are irrational, for which f of alpha is 0. And that was kind of like trying to use that
got it.
uncountably infinite idea. And then I kind of said that because f of x is equal to 1 over q, we could reason that like the absolute value of f of alpha minus f of x is equal to 1 over q, which would be less than epsilon, kind of going by that definition.
Yeah, honestly I think you're getting there.
Well, and then like kind of going off of that, I was kind of thinking that like I don't really know what, like I'm missing some lines somewhere, but kind of the idea
definitely.
that if epsilon is less than like 1 over q, then that would mean that like there'd be no delta that could satisfy.
Yeah, could be in trouble.
Yeah, so I don't know. That was kind of where I got stuck.
That's cool though. No, this is good. I'm glad you suffered.
I tried.
That's all.
Yeah.
That's really all I wanted was the suffering. Let's talk a little bit. Honestly, did anybody else attack this one? No, this was probably one of the hardest problems of the semester, I would think. I think a sequential approach is probably better. And it's gonna come back to this trick you've seen me mention like 5 times this semester. So what's t of pi?
0.
Right, because it's irrational, definitely. What's a sequence of rationals that approaches pi? So give me a sequence. So x of 1 is, we'll start chill.
3.
Yeah, what's x2?
3.1.
0.1, cool, and then, right, onward and onward. So x3 is, and you probably might even see where this is going. So now, remember what it means to be continuous, the sequential definition. So we would say t is continuous at a point x naught if we have a sequence of points converging to x naught, and that implies t of x of n converges to t of x naught as well, right? So that's sequential definition, that if my inputs are converging to a point, and this point is in the domain. Luckily here, our domain is all the reals, so as long as we've got convergence, we're converging in the domain. And then this converges to this solid value over here. So let's take a look here. We know that t of pi is 0. What is t of x1? Just 1, because it's 3 over 1. Yeah. And then this guy here is 31 tenths. So what's t of x2? 1 tenth. What's t of x3?
100.
Mm-hmm. Where does it look like those t's are converging?
To 0.
Kind of looks like they're headed to 0.
Okay.
So think about this. I can get, so you give me an irrational. I don't want to use the letter I, but we'll call it, you called it something. I liked it. It was just X. Alpha. I like it. So alpha is an irrational. I can find a sequence of decimal approximations to this. So I know that there exists this q sub n such that q sub n approaches alpha because of the denseness, and you mentioned that before. Each q sub n is equal to a fraction. Now this is the part that's kind of hard to write out, but each one of these will be a decimal representation of q, but you can also think of it as, we could actually just have it as being a power of, there'll be some weird q, I don't know what, there'll be a different sequence of things on top here. Let's just call them p sub n's. And they're just gonna be integers that come on top here. And they're gonna be less than the denominator. Well, they might be more than the denominator, right? But it's still a sequence of integers. So each of these q sub n's can be written as something over a power of 10, and then t of that q sub n is going to equal, that's going to go to 0. So the trick is that you can approach each of the irrationals as a decimal approximation.
From either rational points or irrational points.
From purely rational points. From purely rational, because these approximations will always truncate, right? So if I take this sequence of rationals approaching an irrational, these will always be decimal things that truncate, so they're not going to be irrational.
Mm-hmm.
But I know that t on those things is shrinking to 0. Because the decimal expansion is becoming infinite and I'm getting more powers of 10 underneath. Does that kind of make sense?
Yeah. Does that kind of go with like the first definition of continuity that we
Yeah,
had with like,
that was definition 1.
so like kind of the idea that like it's continuous because there's like for any sequence of points they like as like x of n approaches like x naught, f of x or n approaches f of x naught, and like kind of the idea that like you could have a sequence of rational or irrational like points, and either would converge to zero.
Correct.
And that's
Yeah.
why the irrationals are continuous.
Exactly, and you might, yeah, I see, so yeah, you're right, I might have the sequence that has some irrationals in it, it might be like a little bit of this, a little bit of irrational, but luckily T of an irrational is zero.
Yeah, so like regardless, it's going to converge to zero.
Exactly,
Okay.
yeah, so the upper bound on this T sequence that I get will be something that is still converging to zero.
That makes sense.
Yeah.
That
That's
makes
good,
a lot
that's
of
good, that was good work. So that's a cool function, that's pretty crazy. Seems like this should be easy to achieve. We just got one that's discontinuous, like on the biggest infinity we can find on the line. Seems like having it at a lesser spot should be easy. You can probably tell by the way I'm saying that maybe it's not that easy. So I leave that question with you. We can talk about it. Does that help, Christian? Do you feel like
that helps a lot?
and whatever you got? I'm curious. I'm very actually looking forward to seeing what you got.
It doesn't make a whole lot of sense.
That's all right.
Yeah, I think I was thinking about using like the sequential kind of
Yeah.
like iterations for like irrational numbers. I was like, this is too simple. That wouldn't make any sense.
No, it's kind of a cool idea. Honestly, I've never
Yeah.
seen it done like that, and I think that sounds like a cool.
You
might have something that's about right there.
I think there's might be something there,
I
because it
think
does
so,
feel
too.
like kind of in the way that it was fitting together, that like there was something that kind of like pointed to.
It felt similar to what
Yeah.
we were doing.
It's
Okay.
just I was missing like too many parts for it to really be like super airtight.
Gotcha. Gotcha. Cool. Yeah, I'll grab those. Make sure to help me grab those after class.
Of course.
Yeah, that was the first thing I wanted to talk about. Let me ask you another one, friends. How about this function? Today's kind of pulling some stuff together. We're gonna slow down just a little bit. We're doing that in Calc 3 too, by the way. We're just like slowing the fuck down. Gonna actually try to like assimilate some things. So I'm curious what you think about this function. If you've got a calculator, you might want to graph it too. Having a graph of a function is always helpful. Take a look at that. Is that function continuous? If not, where? Is it discontinuous? And prove that it's not continuous. I'll be right back. Hint, it's not continuous somewhere. You can probably figure out where. pretty weird, pretty crazy, yeah. See if I can get a similar one. And it's hard to picture it if you don't have that graph. What's the domain of this function? The natural domain.
Reals excluding zero.
Sounds good to me. If I asked you what the domain of 1 over x was, you'd say everything except 0. I hope you'd say that. And then that gives us, since sine is good everywhere, the trouble spot comes from the 1 over x. So it's the reals minus 0. Awesome. So we know it can't be continuous on the real line because this 0 isn't even in the domain, so I can't talk about continuity everywhere. Let's think back to that argument about f is continuous at a point. Let's use little x tilde. So f is continuous at x tilde if, got a sequence of points converging to x tilde, f of x sub n converges to f of x. What's happening here? What is the collection of all possible limits here? So take all sequences that converge to 0. Where does f of x sub n converge to? Now we know that it can't be continuous at 0, but I'm just thinking, if we were going to define it, maybe I could come up here and go, when x is not 0, and then I could define it to be something right here when x is 0 and make it continuous. Maybe I could do that. Give me a cool sequence that converges to 0. One over n, thank you, love it, thanks. So, f of 1 over n, what does that look like? Well, that looks like sine of 1 over n, that's a sine of n. Kind of hard to compute. What could we do to tweak this so that it made it, because sine is, like, I don't know what sine of 2 is.
Throw a pi in there.
Throw a pi in there. We get some pi action in there, then we can do some work. Where should I put the pi?
Like, is it coefficients in the ends? So
Yeah.
do 1 over pi n.
Yeah, I like it. And now we got n pi. All right. What is n pi, sine of n pi?
0.
Nice. Okay, so let's check out what we got here. We've got a sequence, 1 over n pi. That definitely converges to 0 as n goes to infinity. And we have f of 1 over n pi equals 0 for all n. So that's cool. So this thing definitely is also converging to 0. It's always 0. So maybe I should just put a 0 here and be good. Now that function's continuous. Or are there other possible limits that I could get out? Can you give me another one that might not come to 0?
1 over pi, like half, like 1 over pi over 2 plus pi n.
I like the way you're thinking. So you're just thinking, I think you're thinking about these guys right
Yeah.
here. Yeah. So think about how a sine function works. When we're at pi over 2, when we're at 5 pi over 2, it's 1. Got the periodicity here. So if we can get this thing inside here to be those multiples of pi over 2, then we're good to go. So let's think about that. It's a sine of, how would we write that? How would we get these multiples? Let's see, where's the next one? It's back here. What is that, negative 3 pi over 2? Is that right?
Yeah.
Yeah. Give me a sequence. Sine of what equals 1?
Pi over 2 plus 2 pi n.
Cool. That's a great way to do it. Just tack that on there. And so that's going to be 1 all the way. And then let's get this as one solid fraction. So that's sine of pi plus 2. I'm going to multiply that by 2 over 2. 4 pi n over 2, like that. And that's equal to 1. And then just one more little tweak, that's sine of pi times, yeah, let's leave the pi on, I guess we'll just leave the pi on top. Pi times 1 plus 4, like that over 2. So if I make my sequence the reciprocal of that, so if I come over here and I say, okay, what about f of 2 over pi times 1 plus 4n? Then I'm going to get out sine of the reciprocal. And I know that that's always 1. But 2 over pi, 1 plus 4n, where does that converge to? It goes to 0. However, f of 2 over pi, 1 plus 4n, is constantly 1. So it does not converge to 0. Can I get a sequence of points converging to 0 that converges to any value inside here? And the answer is yes. Do you see how we could just pick, you want to converge right here, you want a sequence that converges here while its inputs go to 0, just grab all these values at that height. Grab half of them, whichever one's easier. You can get every single point between -1 and 1 inside there. So if you were going to close, if you were trying to make this thing continuous, you can't do it by adding a point. You'd have to add a whole line and then it's still not continuous. So good. Good work. Let me ask you this. What about this function? About that function. Where is that function continuous? Think you got something, Cormac? Kind of look like you do, but
Yeah, I think it's continuous on the wheels.
yeah. So what's your argument? I agree.
The limit as x of n goes to 0
guess I was just thinking like the limit as it goes to 0, the function also goes to 0, and I can't think of another spot where it wouldn't go to like a different number.
Yeah, definitely. So we took that thing that was nasty before. The only trouble we had was dividing by 0. And now we added in, well, we multiplied by this x. And so what that had the effect of doing, remember how this function looked like this? It got closer and closer, it just vibrated more wildly. We put an envelope on it. So we took the function y equals x, and we multiplied every value of this function by that fractional amount. So what, if you take a look at the graph of this thing, what you see is this happening. You see it whittling down to 0. So this thing controls the amplitude enough that we get continuity at 0. And in fact, we can go back to some old Calc 2 and just look at the limit of this function as x goes to 0. Let's do it together. Let's remember some Calc 1. You look ready for some Calc 1. So this part's going to 0. This part's going to infinity, kind of. Let's put a plus on it so that at least I can claim that. So, this thing's not going great. This isn't looking good. What if I rewrote it like this? Sine of x goes to 0, sine of 1 over x over 1 over x. I don't know. I guess I was thinking we could L'Hopital it, but now I'm starting to think that doesn't really cut it. Yeah. I was thinking we could show that this limit is 0. Oh, we don't need all this fancy stuff. I'm being crazy. Sorry. Just being the Cooperman. So, we got that, right? We know this much, that no matter how crazy and batshit this thing gets in terms of its internal oscillations, this is always true. So if I multiply through by x, get that, squeeze through. So now, just thinking about the fact that as x goes to 0, this goes to 0, as x goes to 0, this goes to 0, we get that that must go to 0 as x goes to 0. So anytime your input sequence is going to 0, your output sequence will also go to 0. So, yep, I agree with you, Cormac. This is continuous everywhere, including at the crazy point where things are oscillating madly. All right, I got some other intuitive questions, things to intuit. So here's a challenge. So let's assume that f is continuous, and it's continuous on the reals. Let's build up some intuition. So I'm going to ask you some things. Is f of a bounded set bounded? Is f of an open set open? Take a minute and explore these things. And what I would do is draw some pictures, think of some graphs, and do graphical thinking to try to break these, if you can. Try to break these definitions. So you're gonna like come in here and say, all right, I'm going to take a bounded input on a continuous function. Can I make that unbounded? Can I make f of an open set closed by picking the right function? And if not, then we might want to try to prove it. I got one. Let's just stick with those 3 and we'll put them together. Take a few minutes. A little bit of a kind of working day today. pictures is your friend. Wow. Do you guys want me to bring tea for you? I can start bringing tea for us. Bring a cup, pour tea in it. Bring my teapot, make tea in here. Do that. I think that sounds nice. Truly at the like not giving a shit point of the semester for sure. Just like, let's just do different things that are fun. We're all tired. If you get something, let me know and I'll come check it out and see how you're going. And you don't think of nothing has to be crazy. You don't need Tomei's functions. These are anything that would break these are things you can totally, you have seen in your life many times. And I will tell you that only one of those is true. Got anything? Maybe? What you thinking? Yeah. But that's not continuous. So I agree that, but the F, we're assuming F is continuous.
Oh.
Yeah, that's great, that's an awesome job, yeah, if F is allowed to be any function, gets a little trickier when we require continuity on the function.
No.
No, okay, okay, that's good, this is the thinking is the important part. You got something?
Same thing as him.
What? Yeah.
One of the text for the first one.
Oh, yeah.
But that's not continuous.
Well,
Right.
oh, yeah. Maybe yeah, that could be tough. This probably, I need to tweak this a little bit because now, just based on the question you asked, because a continuous function on all the reals, well, we could just do like f of x is x. That's not bounded. But having a bounded set input, so let's take this off a little bit. It doesn't have to be continuous everywhere. Maybe f just goes from some domain D into the reals. This might help. Is f of D bounded if D is bounded? That was good. And this one can be any subset. Yeah, so then your first example, that, because that was kind of the example I was thinking of in my head, but
Mhm.
that's not continuous on everywhere,
Yeah,
but if we can restrict it, so then did you?
totally. I've done this one.
Okay, but yeah, so if you did this on like 0 to 1,
Exactly, like you still get like the.
it's bounded, but it's on, then the output's unbounded, yeah,
Totally.
yeah, okay, cool, so yeah. Good. So for that first one, the kind of thing I was thinking about is a function that is asymptotic on an open domain. So f of x is 1 over x. If you take out the 0 and make it 0 to 1, then your output set gets stretched to something that's totally unbounded. So boundedness is not preserved. So continuity does not preserve boundedness. Boundedness alone is not preserved. There's actually, we're gonna get it, but we have to do something else. Anybody got? So that one's false. That one is not true. One of these is true and one of these is false. Do we have any ideas? What you thinking?
The true one is that if it's closed, it stays closed.
Yeah, it is. Yeah, why?
Because I also took the same, like the open interval 0 to 1,
Yeah.
and I mean, you can input a 0 and get 0, or you can input a 1 and just get whatever number you want.
Yeah.
Kind of what I was thinking.
Yeah, your intuition's totally right, that this one is true. So let's actually prove it. Let's so assume that f is a closed set, subset of the reals, and we have f is continuous on that function, on that set, f. So we want to show that f of big F is closed as well. How do I do that? How do I show a set is closed? One way, right? There's a bunch of ways. Oh yeah, that sounds painful, especially with functions. Yeah, that's definitely a way, but oh man, brutal. But I agree. What's like a, yes?
Every sequence in a set that converges to an element implies that element is in the set.
Solid. So let's work with convergent sequences because we have that continuity link to sequences, and that's going to allow us to kind of link things together. So let y sub n be a sequence of points in f of f. Let's draw a picture too. Always helpful to have pictures, sometimes misleading. So here's going to be my function, my set f, and then I've got some weird function. And the output is this. This is f of f right here, this interval that I've got up here. Now this drawing's super suggestive. We still can't, I drew it closed, but I can't assume that. But it's gonna help me get my point. So I'm just gonna pick a sequence over here. y1, y2, blah, 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 y, so on. And then these are converging to somewhere in here. Let's say they're converging to y tilde. So let y sub n be a sequence of points in the image of f. Y sub n converges to y tilde. I'm like apparently on tildes today. I don't think I've used tildes all semester, but you watch one math video and it can pollute your brain. many ways, and I watched several this weekend. So we've got this. So y sub n converges to y in that. How do I get back to f? How do I move from a sequence of points here converging to a sequence of points back in f? Because f is all I understand. How do I move backwards?
Inverse.
Yeah, kind of, yeah. Yeah, and we might not have an official inverse function, because this thing might be, you know, not one-to-one, but we can pull back the images. So this is a very common trick. What we can do is say, okay, well, if there's some point y1 here, then there must be some x1 down here where it came from. Everything up here was mapped by the function from some point in that set. So for each n equals 1, 2, there exists x sub n in f such that f of x sub n equals our y sub n's.
Does that kind of pull on like that epsilon delta definition of continuity then? Like y's being like the call and the x's being like the response?
Yeah, yes, absolutely. So now we've got this sequence of points. It's a sequence of points in F. And F is closed. I'm starting to actually wonder about this guy right now. And it does feel like it's true. I'm pretty sure it's true. So we get that sequence of points in there. Just draw it. Maybe that'll make me feel better. x1, x2, Now, how do I get those points converging to something? That's what I'm starting to wonder here right now. How do I know the x sub n's converge somewhere?
Will you use your, because it's continuous, so if they converge, then their outputs also converge, or something like that?
Yeah, definitely. So we do know this. We have that if x sub n converges to x, then f of x sub n converges to f of x. Absolutely. But I've kind of got this part here, right? I've got the assumption that this is a sequence of points up here that is converging. And they are f, so I've got f of x sub n converging to y tilde. But that doesn't necessarily give me backwards, right? I've got this implication forwards. So I'll tell you what I'm thinking here. If f was bounded, if f was closed and bounded, I could invoke what theorem to get? So if f is closed and bounded, I got a sequence of points in f. How can I ensure that there's a subsequence that converges?
Remember the name of the theorem?
Heine-Borel.
That's what it is.
So if I also know that f is bounded, where's my eraser at? If I know that f is bounded, and I've got a sequence of points in it, so let's just kind of talk this through here. If f is closed and bounded, what's another word for that?
Compact.
Thank you, i.e. compact. Then this sequence of points that we constructed in K has a subsequence x sub n sub j such that x sub n sub j converges to something, we'll call it x tilde in K. And then f is continuous f of x sub n j must converge to f of x tilde. And that f of x tilde must be y tilde, because that top sequence, this is a subsequence of our original sequence. It converges to y tilde. Our original sequence converges, so if the subsequence goes to this limit, everything must go to this limit, and this must be the original limit of our series. But I'm starting to wonder about the f of a closed thing is closed. So, I'm kind of wondering about this. I thought this was true, and sadly I didn't actually do the digging. I just thought, oh, that's definitely true, that f of a closed, if a continuity preserved closedness, I was thinking that was true. I'm starting to wonder, because what I can say for sure is that, this is for sure, that if K is compact, then f of K is compact. And I kind of just did the proof right over there. You take a sequence of points here, pull it back to here, get a subsequence. That subsequence has a limit, and then you can basically almost have the proof of this right over there. So this is a fact here. This sure feels like it has to be true, but the proof of it is feeling a little elusive to me right now. Let's go to this one. I'm gonna hold off on this one. This is a fact. This is 100% true. This I'm feeling about.
Wait, why couldn't you just
Yeah.
go back from the hyperbola? I guess is it?
Yeah,
because
help
it's
me
not-
out. Maybe we can pull this together.
I guess you would need the if and only if for to go backwards
Yeah.
with the hyperbola, because could you have a compact sequence that's not necessarily closed? Or does closeness, does that imply, or does compactness imply that it is closed?
Yes, so compactness gives us that it's closed, so that means every sequence will converge in it.
So if you prove compactness, couldn't you just assume it's closed as well off of that?
Definitely, yes. But I'm just wondering if I could assume that the set is closed, but not just closed, if I don't know it's bounded as well.
Oh.
For compactness, I have to have closed and bounded.
Yeah.
Actually, okay, hold on. I don't think this is true. No, I'm gonna have to come back to it. Sorry, come back to that one. That's pretty bad, but yeah, right now I don't know, but I do want to hit on this one. Anybody got anything on that one? Because that's false. For sure. Does anybody have a sense of why that's false? Cormac, did you come up with an example?
You had an open set, and then you just make, oh wait, but our functions have to be continuous.
Yes, yeah, we do need, yes. Yeah, you were having fun with that piecewise stuff.
Yeah,
So
if you
here's
were
an
to
open.
just make a piecewise that was just constant, just one.
Oh, that's pretty good.
Yeah, can you not make a
Oh, that's nice. I like that. Yeah, why couldn't you do that? That's great.
It's just one everywhere.
Yeah, absolutely. I was thinking of something much fancier. So Cormac's saying, I could let my set U be, well, hell, it could just be the reals, which is open. And then let f of x be constantly 1. But then f of u is just the set 1. That's good. Yeah, that's pretty good. I was thinking of something like this. I like yours. Yours is so much more elegant. I was thinking of something like a parabola that went like this. So it's like x squared, which is only defined on -1 to 1. And then the output image, you can't hit 0. Can't hit that 0 there because you can't get to the 1 and -1. But you can hit the -1. So for this, if this is f, then f of -1 to 1 is closed interval -1 to 0, half open like that. Yours is way better. Yours just gets to the point. But I'm kind of like, I feel like that's true, that f of a closed set is still closed. Can we freaking prove this? We're gonna start from scratch again. Okay, so we've got f is closed. Show f continuous. Unless somebody can think of an example where the output is open, that's the only thing f is. F is closed. Okay, so let's hold on here a second. So we know that if f is closed and bounded, that it's compact. And f of a compact set is compact. So this would also be closed and bounded as well. Now, I guess, so what if f is closed and unbounded? So for example, I have something like 1 to infinity. Is it possible for us to get a function out of this where the image is an open set? So yeah, like just the range of y values over here is open.
Is 1 to infinity big enough to map to the real numbers?
Say more, please.
So if you like just had a function where 1 to infinity for every number, it mapped to every number of the real numbers, then your output would be an open set. But I don't think 1 to infinity is big enough to do that.
I mean, there's as many reals in here as there are real numbers.
Okay.
So give me your mapping.
So
Okay.
Yeah, I don't know how you would actually do it. Is the only problem.
Do you have
Yeah.
something that like oscillates, like starts at like 1 would equal like 0, and as it like goes outward, it just gets like further from 0,
Oh.
like on each side.
Like the outputs, like.
Yeah. So then like you would that be open?
So we'd be hitting the maxes, right?
Yeah.
We'd be hitting these, so these would create closedness over here. And even if Cormac, even if we could, I like this idea, you guys like working on this, but even if I could get this f that did this, this is still closed. Because every sequence of points that converges in here converges to a point that's in here.
Well then, could you have it be something that like oscillates and like those like it stays bounded on like the interval -1 to 1 for its like outputs and never like hits those but like approaches them, you know? I feel like we did something like that like a
Yeah.
couple weeks ago.
I know what you're picturing.
Yeah, you know what I mean? Because then like
Yeah.
it would be open because,
Yeah.
but it would like,
Huh. Like these were approaching, like the amplitude of this was approaching some open interval,
yeah,
but never getting there, so.
exactly. Like wouldn't that then be like a closed interval going through?
Like this. Okay, so let's see. Okay, this might, yeah, I think, this could work, Well, I'm having a good time. Your mileage may vary today, but this is kind of exciting. So we're gonna create a function that we're gonna do it on, we'll just do it on 0 to infinity, because that's definitely closed, got that nice closed point there. And what it's gonna do is it's going to keep growing in size, but in a way that it starts to limit off and never actually gets to that full size. So, so we'll start with sine. So we got sine, so sine's gonna do this. And now we want an amplitude function that is asymptotic. Oh yeah. So if we can get an amplitude function where this thing never hits those, but it's growing to there, then we're good to go. So what if, you got something?
No.
Oh, okay.
I was gonna say e to the x, but I don't think
Yeah, we could do 1 minus e to the negative x. And then as x goes to infinity, this goes to 0 and that approaches 1. I think we could do that, or we could even just do something a little just less intense. So then this amplitude will never be 1, but it gets closer and closer to 1. Holy shit. Yeah, I think this works. I think this does it because, so this function here, let's just take a look at that. When x is 0, we're at 0. And this is our envelope here. And I don't know, what does that thing look like? Approaches 1, so it kind of does this. Yep. And then when sine is negative, it'll still be grabbing those values for its amplitude. So for example, when sine is -1, it'll just be -1 times that number. And so we can approach -1 down here asymptotically.
Would you be able to like take the sign out?
Yeah.
Like, could you do it a little bit?
Yes.
simpler?
Yes.
Like,
Yes.
like -1
Actually.
to the x times x over x plus 1. Like, wouldn't that then?
Yes.
It does the same thing, but without like having to involve.
It didn't have to be
sign.
so ridiculous.
Yeah.
I know you're not saying that, but yeah, you're right.
Because then like you don't have to worry about like any of the other
There we go.
values that fall in between, and it's
There we
just
go.
like.
Love it. Yeah, we could just do something that's asymptotic.
Because then I think that would like do the thing where it
I think
approaches 1. and
You're
negative
100% right. So yeah, so we could take this function here. So f of x is x over x plus 1. And this is why the proof wasn't feeling like we couldn't get it together, because we can't get it together, because it's actually a false statement. So this is going to map 1 to infinity to 0, which is closed, but then one which is open like that. So let's do 0 to infinity, yeah. Yeah, I think that's it. Damn, that's cool. Huh. So yeah, we had to go to an unbounded example because if your set is closed and bounded, you're compact, and a compact set always maps to a compact set. So, cool. All right, I feel pretty happy about that. Again, different mileages in here, but you doing okay, Liv?
Yeah.
Yeah, okay, cool. That was an interesting expression you had on here. We should probably call it for today. What I would like you to do for Wednesday, I want to finish up regular continuity on Wednesday. If you could please, and I'll have all your stuff graded back to you on Wednesday that I don't have back to you yet. It's the intermediate value theorem that I mostly want you to read the proof of. So that is, what the heck is that? Yes, could you please read the proof of theorem 18.2? That's on page 127, the intermediate value theorem, and we'll talk about that. And if you want to get a little bit of a head start, you could check out uniform continuity, which is section 19. Honestly, it probably wouldn't hurt to just read and have those in your brain, especially because uniform continuity kind of pushes things a little bit further. There we go. I've decided we're just gonna go to wherever we go to. You know, we're not gonna try to cram a bunch of shit in. We're just gonna work. We're not gonna try to go fast. Same in Calc 3. I've decided I had this goal, we were gonna reach some certain place, and now we're just gonna like learn stuff. Just calm the fuck down.